Hello students, welcome to this MOOC course on Advanced Analytical Techniques. So we were discussing about the chromatography, that is unit 3 of this Advanced Analytical Technique course. And we have already discussed the principle of chromatography, various fundamental terms arising in it, and we have also discussed the column performance and then optimization. And now we are on the last part of this course, chromatography part, and today we are going to discuss various effects of certain factors on the resolution, and we are also going to see certain individual parameters which affect the column performance in terms of its resolution. So let us begin our journey. So in this series of lecture we are going to revisit or reintroduce the concept of resolution. Then we will move forward and we will look into the retention time and its significance and its relationship with the resolution. Then we will see certain factors which affect the column performance, then certain equations and the related graphs. Then we will see certain insights, then we will do certain problems, and finally we will draw certain conclusions, and then we conclude with a summary. So let us embark on this exciting journey of resolution of various components by a column chromatography. Okay, let us move. Now, chromatographic separation. This is the most important part of any separation with regard to elution chromatography. So, chromatography is actually, it's a dynamic equilibrium where the solute molecules forms or gets interacted with the stationary phase, and depending upon the interaction with the stationary phase, they actually travel with different speeds, their migration rates become different, and because of the difference in the migration rate, they elute at different times, which is detected by a detector in terms of responses as peaks, and that chromatogram is called as the pictorial representation of peaks of various constituents of a given mixture. So this picture, this figure actually shows you a two component system with two retention times, that is TR1 and TR2. Now you can see that in this chronogram you can see a visible difference between the two peaks. That is, you can say that resolution, which is represented by RS, is good. Similarly, you can see that this distance, which is depicted by W1, and this distance W2 is called as peak width. Now, for an effective chromatographic separation, there are two important parameters. Number one is that rate of width of peak should be as small as possible, and at the same time the distance between the two peaks should be as large as possible. So if these two things are satisfying, then you can say your column is optimized and your column is efficiently working. That is, your column is actually effectively separating the components of the mixture. So while doing so, we will be studying certain key parameters with regard to the resolution of different constituents of a mixture. So we will be looking into it, the retention parameter, that is the retention time, resolution, selectivity of the two components separating on a particular stationary phase. Then we will be talking about the efficiency, which is depicted by N, and the capacity factor. This capacity factor is nothing new, but it's actually the retention factor. It is the retention factor. Retention factor, and it is given by K dash. This K dash is actually can be defined as TR minus TM upon TN. This Tm is actually the dead time. This Tm is actually the time taken by the unretained solute, and Tr is actually the time taken by a particular component. So we are going to study each of these parameters in detail. Now, one thing which we have to remember, that for an effective resolution or effective separation, the two things must be satisfied. That is, the width of the peak should be as small as possible. That is, we have sharp peaks, sharp and narrow peaks. And the second thing is that they must be resolved. That is, the distance between the two should be as large as possible. We have already seen in our previous slides, we represent this by delta Z. Okay, so this delta Z actually is given by TR, here TR2 minus TR1 upon the distance, which is W1 plus W2. Okay, so this is actually twice of TR2 minus TR1 upon W1 plus W2. So let us start with it. So here our previous equation. So resolution can simply be defined as the distance between the two peaks. The distance between the two peaks, which actually, because of the two component. If we have a three component system, then we have 1, 2, 3 peaks. So most of the time the number of peaks actually tells you the number of different constituents present in the given mixture, which is to be separated. So you can see that here we have TR2 minus TR1. Now this TR2 is actually that component which is eluting at a low or at a later time. For example, in the previous slide, if you see that this was a TR2. So this was your start point. This was your start point. Initially, if you draw a diagram, you will always see this. This is actually, this is the TR, or you can say this is TM. Okay, that is the void time or the dead time. It represents the time taken by the plane mobile phase to elute from that particular column in which the separation of different components is going on. For example, here it is the component 1 and it is component 2. So the distance should be as large as possible. Okay, so the resolution is actually the measure of the degree of separation between the two adjacent peaks. So this RS is actually defined by twice of 2 into TR2 minus TR1 upon W1 upon W2. Since this W1 is the width of peak of component 1, W2 is the width of peak 2, that is component 2. And this actually has a very good significance. This TR2, as I have told you, for example, if you have a chronogram, then this is actually the case. This is component 2 and this is component 1. This is the retention time here, retention time. This is the retention time. And if you plot it here, the detector response, the detector response. Now this distance, and here you also get some TM. So this is actually called as the TR1 because it is component 1, and this distance is called TR2. Now this TR2 actually tells you that this component 2 is eluting at a later rate. That means that component 2 is having more, or you can say stronger interaction with the stationary phase as compared to component 1. Or in other words, you can say that component 1 has a stronger interaction with the mobile phase or the eluting solvent. So how you can define 2 and 1 component? That 2 component is that component which is having the highest interaction with the stationary phase, and component 1 is that component which is having the highest interaction with the mobile phase. So for a better resolution, there is a number. Actually, this RS is actually a dimensionless quantity, is a dimensionless. It does not have any units. Dimension. Let me write it more clearly. Dimensionless. Dimensionless quantity. And for a resolved system, RS must be greater than 1.5. Okay. So RS must be greater than 1.5 so that we can have well resolved peaks. If RS is less than 1.5, then there must be some overlap. And as the value of RS decreases or goes towards 1, the overlapping increases. The overlapping of peak increases like this. Lesser with the value, greater with the overlap. And at one point of time, the two peaks converge, which we are going to see in our next slide. So here it is. So here in the first one, you can see that RS is actually less than 1. That actually this big peak is actually engulfing, it is engulfing the two peaks pertaining to two components. Now the moment, for example, here it is again this RS or the resolution here in this case is again less than 1.5. So again this is, here the resolution is actually a little close to 1.5. So this is actually the correct value. Okay. So here the resolution is close to 1.5 and you can see that the component, for example, A and B are well resolved. And this resolution is important because it not only gives you that the two components are converging or eluting at the same time, but it also creates a situation where you cannot quantify the two components specifically. So for quantification, what you have to do, you have well resolved peaks, because the area under the peak actually tells you about the quantity present of that particular component in that particular mixture. Okay, so you have to make sure that your peaks must be well resolved and the width of the peak should be as small, should be as narrow as possible. Ideally, the peak should be Gaussian type. Ideally, peak should be Gaussian peak. It should resemble with the Gaussian peak. Okay, so let us move forward. This is an ideal peak. You can see that this is an ideal peak where if you drop a perpendicular, it is telling you that TR is equal to 10 minute. Similarly, you can see the TM. This TM actually implies that this is the peak for the pure mobile phase without solvent, pure mobile phase. So this distance actually, this distance is TM. Now there is one important, very interesting case. You can see that for TM we have shown it with only a dotted line. TM is shown by only a dotted line. It does not appear as a peak. And if it is a peak, then it must be as narrow as possible. Why it is narrowed down? Because this shows that your mobile phase is having no interaction with the stationary phase, and that must always be there. Okay, that your mobile phase have zero interaction or no interaction with the immiscible stationary phase. The moment it starts interacting, the whole efficiency, or you can say the whole process of separation by chromatography gets compromised. So this distance is TM and this distance is TR, and the distance in between this is called as TS. Okay, so what you see, the relationship is here. TR, it's a simple thing that TR is equal to TM plus TS. Then this TR gives you the retention time for the solute, TM gives you the retention time for the pure mobile phase, and TS actually, if you think of TS, then TS is actually TR minus TM. That is, TS is actually giving you the retention time by the stationary phase alone. Okay, and that is actually the thing which we have derived from TR is equal to TM plus TS. So the greater the time of interaction with the stationary phase, the greater will be the time it will take to elute. That is, the solute peak will take the maximum time. So here time is money actually. So retention, now we can calculate it in terms of K dash, which is the retention factor or capacity factor, and this K dash is equal to simply TR minus TM upon TM. Okay, so this is the retention capacity or retention factor, or sometimes it is also called as capacity factor, and we are going to explore this retention capacity or retention factor in our coming slides. So now the things are clear that Tm is actually the time taken by the solute molecules, by the solvent molecules alone, and Tr is the time taken by the solute molecules through the mobile phase. Okay, so let's move forward. Now let us draw a plot with regard to the resolution, that is Rs, versus the retention time, that is Tr. Now you can see that we have plotted Tr, it is Tr actually like this, and it is the resolution Rs. Now you can see that as you increase the time, that is the retention time, as the retention time for the elution of solute molecule increases, then you can say there is an exponential rise of the resolution, and after a certain point of time, which is shown by dotted line, it becomes almost constant, that it does not increase as much as it increased before the 10 minutes of time, that is this. So the resolution actually increases with the time, that is the retention time. So now we have a relationship that resolution increases with increase in Tr, but after a certain point the Rs becomes almost constant, that is Rs does not increase too much with the increase in the Tr. For example, here we have seen it. Okay, now in the next slide we are going to draw a line of optimization. But before going to the next slide, let us discuss one important aspect, that if you have longer Tr, that is if you increase Tr too much, then one important aspect also comes into play, and that is actually the run time. That is, if Tr is too much, then your separation will be taking too much time. Okay, so you have to restrict the separation time also. So that actually leads to lower throughput. That lower throughput means that you don't actually you cannot run large amount of sample if you have a longer run time. Although resolution would be good, but your column will take more time to separate your components. So your column actually does not be good for doing large quantity of separation, that is lower throughput. Now Rs can also be defined in terms of the efficiency of column N, and in terms of selectivity factor, that is alpha, and in terms of capacity factor or retention factor K dash. And the relationship is that if you increase the resolution, then number of plate increases. Similarly, alpha increases. Alpha is actually the alpha can be defined as, for a two component system, it can be defined as Kb upon Ka for a two component system, that it gives you the relative interaction of different components with regard to each other. Okay, so alpha can be defined as Kb upon Ka, that is it is called as the retention factor. It can also be defined in terms of the distribution constant, that is called as Kb upon Ka. Now you have to keep in mind that B component is that component which is eluting at a slower rate as compared to component A. That is actually the trick here. That is, B component is that component which is taking too much time, which is having strong interaction comparatively with with the stationary phase. So the moment you increase the resolution, the number of theoretical plates increases, or the length of the column increases. Similarly, the retention factor or the capacity factor also increases. So this is actually the balance which we have talked just few minutes before, that there is an optimal balance where the resolution is maximum with regard to the minimum retention time, because you cannot extend retention time too long, because it will going to take the separation will be done too long. So there is an optimum balance which is shown by like this, close to 1.9 to 10. This is the time in which the resolution increases very sharply. This is time. So this is actually a trade-off. This is called as a trade-off between resolution and analysis time. That is, just like the Van de Meter equation which we discussed in the previous slide, there was an optimum velocity. That optimum velocity was at that point where B upon U was kept minimum, and at the same time Cu was also kept minimum. So that was the optimum velocity. Similar is the trade-off point between the resolution and the TR, that is the retention time. So in this range, you have an optimal balance. So your TR should be effectively somewhere between 1.9 to or it's somewhere between, it's for example, if it is 2, then somewhere between 2 to 10. Here it is written for a practical balance. So if you increase the retention time, then higher RS but slower separation. Okay, so retention time will be increased, okay, resolution would be good, but at the same time you have to run your column for a large amount of, you can say for a large amount of time. So you have to have a balance between the efficiency and productivity. And in HPLC, what you have to do, you have to optimize this condition when you do certain quality checks of pharmaceuticals or pharma drugs. So here it is, here you can use this trick of trade-off between the resolution and the run time. So now we have a very good table where we have summarized our resolution, analysis time and the nature of the peak. So you can see that here it is the capacity factor, here it is capacity factor, or you can say retention factor, whatever you want to say, both the terms are same. It is retention factor. So it is the capacity factor, how the capacity factor affect the resolution, and what is the actually effect on the analysis time, and how about the sharpness of the peak, that is what type of peaks we are going to obtain. Now if k dash is less than 1, then the resolution will be poor, that is the peaks will not be separated, the peaks will be somewhere like this. Here we have this type of peaks, and of course broad peaks. Now in terms of analysis time, that it is good, this factor is good, but the resolution is compromised. So this is bad with this, but it is good with this, and the broad peaks are are generated, which is again a bad thing, because you need a narrow sharp peaks for an effective, or you can say for an optimized column. Now if your k dash lies somewhere between 2 to 10, then the resolution will be fine, then resolution will be optimum, that is here RS will be greater than 1.5 here. Analysis time would be somewhere, it is not be too long or it not be too fast, so it would be moderate, okay, it's fine. And again you have very sharp peaks are obtained. But the best thing is this, if your k is greater than 10, then excellent RS, that it is somewhere greater than 3, that is called as excellent RS. Again you will get very sharp peaks, ideal peaks you will get like this. Okay, peaks would be sharp, narrow peaks, that is here the bandwidth is rate of peak width is a small, very good, very nice, but this is the problem here, that is you have to run your column for separation for longer times, that is actually problem. So commercially you cannot use this type of thing. Okay, in lab it's fine, but commercially you cannot afford longer times, because you have to do so many separations at the same time. So this is the actually issue with good retentions. Okay, now let us see some real life examples. For example, if we are going to separate caffeine and theobromine, then if we are going to increase the solvent polarity, then k dash actually decreases, and because of the k dash the retention decreases. The retention decreases, and because of decrease in the retention, the resolution also decreases. Then we cannot have good separation. But at the same time, if you adjust your pH, then if you increase the pH of your medium, then what happens is k dash increases. K dash, that is the capacity factor or the retention factor, retention factor increases, and because of this the resolution will increase. Now you can have a very good caffeine and theobromine peaks, well separated just by adjusting the pH, by just adding the acid analyte. So you will get the well separated peaks. So this is actually the interplay where you can use certain factors to have good resolution of your components. Now the column efficiency, we know that the number of plates, which are purely a theoretical concept, that is the which is given by the plate theory, which talks about theoretical plate, theoretical plates which are continuous in nature, and on each plate there is an equilibration between the stationary phase and the mobile phase, and once the equilibration is done, your solute goes down to the next continuous phase, which we have already discussed this in our previous slides. Now let us look at the efficiency in terms of plot. Now you can see that we have red, yellow and the green one. Now you can see that in case of the red peaks, the resolution is minimum because these are broad peaks, and you can say that the peaks are not resolved. This, if you draw this peak, if you interpolate, then you can see that this area is coming under common. So this common area, it is actually restricting your quantification of the two components. So in order to have a good quantitative idea, your peaks must be well separated. You can see that yellow and green peaks are well separated. They are actually touching the baseline. You can see that you have a baseline separation in B and C. So for an effective separation, you must have a baseline separation. So efficiency actually measures the sharpness of peaks, and the number of theoretical plates can be given by 16 into TR upon W square. TR is the retention time. For example, for this peak, if you call it A, component A, then this is the actually TR. From here to here, this is TR of A. This is TR of A. Similarly, here to here, it is TR of B. So you can calculate the number of theoretical plates for each column, and the moment you increase the length of the column, what happens is the width actually decreases. That is, higher than number of n, narrower will be the peaks. That is, sharper will be the peak. That is, more resolution will be there. So you have to look for two things. You have to look for the width of the peak, and you have to look for the distance or difference between the two peaks. So you have to minimize the width and you have to maximize the distance. That are the two important factors with regard to the column optimization, or with regard to deciding the efficiency of any separating column. So the relationship is n is equal to 16 TR upon W square, and we are going to use this equation when we do certain practical problems.